What would actually happen if you stepped into an elevator and dropped straight through the center of the Earth? You might think you just fall until you slam into the other side, but something way stranger happens. First, we need to understand what is gravity doing inside the Earth, because outside the Earth, gravity pulls you with this equation. But that formula might need to change a bit once you are inside. So imagine you are already falling down the tunnel. You are now surrounded by Earth in every direction. So what pulls you here? The key idea is only the mass closer to the center than you actually contributes. Everything outside your radius cancels out. Now assume the Earth has uniform density. That means mass is proportional to r cubed. Plug that into Newton's law. So the force scales like this. Wait a second, that's linear like the force law of a spring. So instead of gravity behaving like normal, inside the Earth it becomes like a spring, which means this isn't just falling anymore, this is oscillation. Now let's see what motion this force produces. We write Newton's second law, divide by m, and we get the harmonic oscillator. So the general solution is this. Now apply our boundary conditions. So x at the start is equal to the radius of the Earth, and it has no velocity. That gives us this equation of motion right here. So your position as you fall through the Earth is literally a cosine wave. You are not just falling, you are executing a perfect harmonic motion. Now that we know the motion is harmonic, we can ask the question everyone actually cares about. How long does it take to get to the other side? And this is where harmonic motion becomes really useful, because once you know something oscillates, the next thing you want is its period. So if we can calculate the period, we automatically know how long one crossing takes. Now the formula for the period looks like this. So what is this omega here? Remember Newton's second law? We see that omega is the square root of k over m. Let's skip fast forward over the derivation. Just pause the video if you want to see the details. In the end, we get this equation with only constants in it. Now we can calculate the period. So plugging in the Earth's parameters into omega, and we get that the period is around 84.39 minutes. But that's the time for a full oscillation. To go from one side of the Earth to the other, you only need half of that, which is equal to 42.2 minutes. So falling from one end to the other wouldn't even take you a full hour to complete. But that raises an even crazier question. If you can cross the whole Earth that fast, how fast are you going in the middle of the trip? Because at some point, gravity has been pulling you inward for a long time, so your speed must become enormous. To find that, we look at the velocity, which means we have to differentiate x of t. The sine function reaches its largest magnitude at 1. And we get this formula for our maximum velocity. Now we insert the numbers. That gives us around 28,460.91 kilometers per hour, which is about 17,684.83 miles per hour. That is the moment when gravity stops accelerating it further. Not because the cabin stops moving, but because the gravitational force becomes zero. So at the center, acceleration is zero, but velocity is at its absolute maximum. In the end, we can conclude that our motion looks like this. The orange arrow is the direction of our acceleration. But wait a second. So far, we've been using the cleanest possible version of the problem, falling straight through the center without any rotation. But the Earth does rotate, because now you might wonder, wouldn't the cabin get pushed sideways? Wouldn't the motion become distorted? And that gets even more interesting if the tunnel is not aligned with Earth's rotation axis, but passes through the center at some arbitrary angle alpha. So does all of our nice harmonic motion math fall apart? To answer that, we only need to focus on one thing. Only the component of force along the tunnel can change its actual motion through the shaft. We only care about what survives after projecting everything onto the tunnel direction. And when you do that, the force along the shaft is still proportional to displacement. What does that mean? Let's try to remember Newton's second axiom. We are still oscillating. That's great. So even when Earth's rotation is included, the motion along the tunnel is still harmonic. The main thing that changes is the period. So, rotation changes the timing, but not the basic oscillating character of the motion. The beauty of the harmonic oscillator is still visible.